Okay, so let me start by doing the exercise from last time. And so we started with a multiplicative functional on the space of configurations. And the problem was, the statement was that multiplicative functional times the determinantal measure normalized is again a determinantal measure where pi g is projection onto square root of GL under the assumption that pi is projection onto L. So pi is projection onto some subspace L, and pi g is projection onto square root of GL. And they said that it is easiest to see this for orthogonal polynomial ensembles. If I have an orthogonal polynomial ensemble, so the corresponding subspace L is the subspace of, as we did, is the subspace of projection onto the subspace of polynomials times the square root of the weight, right? So if I have orthogonal polynomial ensemble in n variables, so corresponding, for example, to a random matrix of size n, then the corresponding subspace L is square root times weight times the polynomials, and so it is clear that now I multiply this measure by multiplicative functional. So I take this measure, I multiply by multiplicative functional. This is just the same as putting this multiplicative functional in the weight. Yes? So this is for orthogonal polynomial ensembles, but in fact the statement is that this property holds in the full generality of determinantal point processes. It is not specific to orthogonal polynomial ensembles, and the proof is quite immediate. This is a little observation from 2012, and the proof is quite immediate. So let us just check this. So to check this statement, we would have to check this again against the multiplicative functional, because as we discussed, multiplicative functionals determine the measure uniquely. So I check this against the multiplicative functional, and I write integral psi h times psi g d over the integral of psi g. So, but we remember that the integral of multiplicative functional is a determinant. It is more convenient for me to write not the Fredholm determinant, but the Hilbert-Kalimann determinant. So I write determinant 1 plus gh minus 1 pi over determinant 1 plus h minus 1, g, excuse me, minus 1 pi. And it is immediate that I get determinant 1 plus h minus 1 g pi 1 plus g minus 1 pi inverse. And so this is an operator I get. So this is not quite the projection yet, but let's look. So this is just the multiplicativity of the determinant. Determinant 1 plus a times determinant 1 plus b is equal to determinant 1 plus a, 1 plus b. So, and just now instead of g pi 1 plus g inverse, pi inverse, it is convenient to consider square root of g pi square root of g, and to it is clear, for example, that also I can write pi here, it wouldn't change anything. But in fact, one directly checks that this is indeed projection onto square root of g. Onto square root of g. L, well, let me do half of the verification and leave the other half as exercise. So take psi in this space, so it would be function of the type psi of g, excuse me, square root of g. Phi, where phi is in L. Phi in L. So this is function in this space. Apply here, so multiply first by square root of g. I get g phi. Multiply by this inverse, it is immediate that I get phi back. In fact, if I apply phi to this expression without inverse, keeping in mind that phi is an L, I get g phi. So now apply pi, nothing happens, it's still phi, and, okay, end of proof, square root of g. Phi is what we get. So I checked that square root of gl is indeed invariant subspace under this operator, and the fact that the orthogonal complement is the kernel of this operator I leave as an exercise, but it's checked in the same way. So it turns out that this simple remark with 1, 2, 3 line proof just allows to conveniently to check. Yes, Fabiana?
Can you explain again the second map from G5 to 5?
Yes, of course. So, yes, any further questions? This is very simple. There's really, it's, if something is not clear here, please ask, because it should be clear in every detail. Clear in every detail. It may be something in the notation is not clear, please don't hesitate to ask. So, okay, just gives a very convenient way of checking that two determinantal measures differ by multiplicative functional. And wherein lies the convenience? Let me try to explain this. The convenience of this is that we work not with kernels, but with ranges of the determinantal point processes. And what do I mean by this? So think about your favorite orthogonal polynomial ensemble, I don't know, Chebyshev polynomials. So let's consider Chebyshev polynomials. Multiply by some weight, some simple weight, whatever you want, just a characteristic function of a subinterval or something. So it is completely not clear how to write orthogonal polynomials with this deformed weight, how to write the corresponding Christoffel-Darboux kernel. I don't know how to do this except in very special situations when, for example, W is a fraction linear function where one has formulas of Christoffel and Uvarov. Except such very special situations, I have no idea how to write the kernel, the Christoffel-Darboux kernel. So the point of this simple remark is that I can't do it and I shouldn't do it, because I should work not on the level of kernels, which I can't write anyway, but on the level of ranges, of the ranges of the operator. Checking a relation between the ranges of the operator allows me to establish equivalence of measures. Yes, Alexander. Can you? Maybe I cannot. Can you? How do you write?
New way.
Yes.
So you have new orthogonal.
Yes. But can you write them down?
No, you mean no, because I cannot write them.
That's exactly what I mean. That's exactly what I mean. So that's what I'm saying. So there is one object which I have very explicitly and the other object for which I absolutely don't have an explicit kernel, and nonetheless I can assert that the measures are equivalent on the level of the ranges. Yes, that's exactly what I mean. Yeah. So, okay, now let us go back. So what we wanted to show, where we stopped last time, is that the conditional measures, we were discussing the sine process, but in fact I will make the necessary assumptions clear as we advance. So let's stay with the discrete sine process at this moment. So that the probability measure of the discrete sine process, so let's write it like this. With particle at P and whole at Q, over the conditional measure of the discrete sine process with hole at P, particle at Q, is in fact the product x minus P over x minus Q square. So this Radon-Nikodym derivative of these measures is in fact this multiplicative functional, which is understood, as we discussed last time, in principal value. So there are several questions here. So let me just to make very clear what is happening, let me again consider the example of orthogonal polynomial ensembles. So if I have an orthogonal polynomial ensemble, so again just an arbitrary orthogonal polynomial ensemble, and I fix a particle in position P. I fix a particle in position P. Then this is again an orthogonal polynomial ensemble. There will be one variable less, but so fix a particle in position P at P. So there will again be an orthogonal polynomial ensemble. One variable less, but let's not concentrate on this at the moment. But the weight, so x1 is now equal to P, so there will be these P minus x2 square, P minus x3 square, and so forth, and this goes into the weight. So I will get product P minus xi square, wxi, dxi. Very nice. So now if I fix a particle at Q, I will have the same expression, but with Q instead of P. And now if I divide, so the van der Monde will cancel, and I get exactly the expression that is written on the board. So product P minus Q, P minus xi over Q minus xi square. And the point of this discussion is really that in this argument it is possible to go to the limit. So the point is that in this argument suffers a limit transition, and I should say that it is not obvious, let me just make it clear, equivalence of measures. It is not obvious to go to the limit in a statement that two measures are equivalent. It is very easy to give examples of families of equivalent measures which go to limits which are not equivalent anymore. So in fact, the work of Olshansky, in which I mentioned, in a specific example, carried out similar scheme and proved, in a different example, proved, so the so-called gamma kernel proved a result of this type, a little bit different, using limit transition. And one can open the paper of Olshansky and see there are technical difficulties in passing to the limit in a statement of this type. Okay, so in fact we will not, the argument that I'm presenting does not go through a limit transition, it's a direct argument. It does not do a limit transition, it directly considers the process with infinitely many particles. And the question that we need to address first, the first question is the following: these conditional measures, are they actually determinantal? These conditional measures, are they actually determinantal? Which in fact they are. So this is, this will be the main purpose of the second part of this talk. So just that determinantal property is preserved under conditioning in a much larger context. Essentially, determinantal property is preserved under conditioning on configuration in a subset. But here, let me first formulate a very specific statement, a remark by Shirai and Takahashi, that a determinantal measure is preserved under passing to so-called Palm measure, so under fixing a particle at a given position. So let me formulate a definition. First I formulated informally and then I formulated more rigorously. So we are doing a very brief glimpse of Palm theory. So the Palm measure of a point process, any point process, so given a measure, any measure, measure on space of configurations, on any space. So the Palm measure is a conditional measure, provided there is a particle at P. Particle at site P. So this is well defined in the discrete case. This is not well defined in the continuous case. Effort is needed to define this object in the continuous case. There are two possibilities. One possibility is to define it by limit transition, and one possibility is to define it by using so-called construction of Campbell measure. The problem is it is not possible to write conditional measure subject to this condition because this is not a well-defined condition. There is no sigma algebra with respect to this. This would be the conditional expectation. So the way out of it is to take a point process. Why is that the case? Because a configuration, particles are not numbered. A configuration is a collection of particles rather than a sequence of particles. So the way out of it is to consider the so-called Campbell measure, namely one takes a point process and one marks one of the particles. So one considers the object configuration and the particle of the configuration. So, so one marks one of the particles. The measure, the point process is naturally lifted. Let me not write the formulas and just give reference to my paper where they're all written, but also they're written in Painlevé and in in fact, this approach based on Campbell measures goes back to the work of Olaf Kallenberg. But just let me just say that then, of course, I can just say that I take conditional measure with respect to the event that this marked particle is at given position. And then the Palm measure is well defined. Okay, so, and of course, now I have an audience participation question. So the correlation function, let us recall that correlation function is essentially infinitesimal probability that there are particles at this site. So the question is, else correlation function of the Palm measure, what is it? How is it related to the correlation functions of the original process?
Can I just fix one variable?
That's exactly right. Yes, that's exactly right. Thank you very much. So it is rho L plus 1 of the initial process where one substitutes P. That's exactly right. So it is it is quite immediate to write the transition to Palm measures on the level of correlation functions. And from here one immediately gets a theorem of Shirai and Takahashi. Theorem of Shirai and Takahashi. That transition from that, let me write it like this. Palm measure of a determinantal point process is indeed a determinantal point process with new Palm kernel, and the Palm kernel is in fact rank for one perturbation of the initial kernel. In fact, it is passage, so let me write it explicitly, here it is. It is passage to the subspace of functions which are 0 at given site P. At given site P. Okay, let me write it here. So, so if pi is projection onto subspace L, then pi P is projection onto subspace L of P, which is functions phi in L, phi of P equals 0. So in fact, you can see this. It's always useful to keep in mind the example of orthogonal polynomials, which is this is exactly what it is. This is the subspace of polynomials which are 0 at P. And so this is exactly what it is. Okay, keeping in mind, one might ask me, how is it possible? What does it mean, value of a square integrable function at a point? But in fact, please don't forget that our space is a reproducing kernel Hilbert space. So it has a kernel, and in fact, value at a point is just the inner product with the kernel, with the corresponding function in the kernel. So it is in fact well defined because we consider reproducing kernel Hilbert space. So this is a characterization of Palm measures, the Shirai-Takahashi theorem. Let me just say one thing. just to make clear, so I say conditional measure provided there is a particle at site P. So this particle at site P is then removed. The particle at P is removed. So for example, if you consider Palm measure of the sine process at 0, for example, so I consider conditional measure subject to the conditions that there is a particle at 0, but this particle at 0 I remove it. I remove it. I consider all other particles. So yeah, yes, Fabio.
So anyway, the Palm measure is again a measure of the configuration.
Yes, absolutely. The Palm measure is again a point process, a probability measure on the space configurations. That's quite right. So, and by the Schreiter-Kahashi theorem, it is just a determinantal measure with such kernel. And let me point out that looking here attentively, one notices that this theorem is a theorem that one learns in elementary school, that area of a parallelogram is a product of length by height. Because this is exactly height, right? This is the projection. So, having the length here, and this is the height. And this is the height, so product of length by height. Okay, so please observe that in Palm theory, we are able to both identify the subspace and to identify the, kernel. Whereas now I need conditional measures subject to the conditions that I do not have particles at a given site. So let us consider again. So let us consider some subspace, some subset, B in E. Let's say bounded, and let's consider conditional measure B. Conditional measure provided there are no particles at B. Provided there are no particles in B. No particles in B. So I claim that this measure is again determinantal, and I also claim that the proof is already on the blackboard. So why? Sorry, say again? But maybe it's not discrete. Maybe it's not discrete setting. One could argue by inclusion, exclusion, but it would not. It would require some effort to prove that one gets the determinant actually. And in the non-discrete situation, it's not even possible to argue by inclusion, exclusion. But the answer is literally written on the blackboard, though.
It's just that because there's a projection which is only mapping to the where phi p is 0.
Yes, but no, excuse me. But now I say provided there are no particles in B. There aren't any particles in B.
Yeah, that's what that one should.
Well, no. This is a conditional measure provided there is a particle at a given site. Here I'm considering conditional measure provided that some subset, for example, the unit interval on the line is entirely devoid of particles.
So then just we have a formula for this.
Mm-hmm. Yes. So in fact, okay, I claim that this conditional measure is in fact the original measure times the multiplicative functional.
Yeah, which is that?
No, but not that one.
It is the ratio of two.
The ratio of what? So what? So I say that this conditional measure, what is, again, conditional measure on the subset, let me say again. So what does it mean? Conditional measure, that is to say, the measure P restricted to the subspace X, to the subspace of those X that have nothing in B. So just, there is my phase space E, there is the subset B, and there are some those configurations who hit B, I kick out, and those that don't have particles in B, I keep. So I claim that this measure is equal to the initial measure times the multiplicative functional. Indeed, of the integrator function, thank you very much. So indeed, this is pi b is psi multiplicative function corresponding to the characteristic function of the complement E minus B times P. this completely general statement. The specific statement, however, is that this measure is again determinantal. It's a corollary of what went on before. So determinantal on what? Determinantal is governed by projection, by the projection onto I.e. that would be L. So I can write this projection, I denote it by pi E minus B. I denote it by, I can write it. But already one can see that it is not really possible to write the formula for the kernel. So it is not really possible to write the formula for this kernel. Not really possible to write the formula for this kernel.
Do you want to normalize this?
Yes, I do. Yes, I do. Yes, I do. Yes, I do. Normalized, yes. Normalized. I do. Yes, thank you very much. Yes, I do. So it is governed by this projection, by the projection pi. Yes. So for the second part of my talk, let me point out that the combination of this observation of mine and the theorem of Shirai and Takahashi gives the following point, that conditional measure, which in the discrete case was established by Lyons, so that the conditional measure of determinantal point processes subject to having the condition that at some bounded subset B, the particles are exactly these ones. So I denote this conditional measure by pi by pxb. So what does it mean? Conditional measure under the condition, measure under the condition, that the restriction, let me write here y, that the restriction of x onto B coincides with y. So this is exactly the condition, coincides with y. So this is it, y. Here it is. Yes, so that in this part of the phase space I have such and such particles and nothing else. So please observe that these are particular cases. So I say that I have a particle at P and no particle at Q. But this is general definition which works both in the discrete and in the continuous setting. So, and I have proved that this is indeed determinantal. Is again determinantal, just I have proved this on the board, because in fact I just need to take first Palm measure. So it is possible to iterate the Palm construction. So I take L of P, then I take L of PQ, then I take L of PQR, and so on. So I iterate the Palm construction. But observe also that then at the end, when I have exhausted all the particles, so plucked them out, I'll just condition on the condition that there are no more particles. And this is this. So it is possible to write explicit, very explicit formulas, and again, this is written specific. It's an exercise, but one can see it in joint paper with Xu and Sharma, for example. They're written explicitly. In the second part of this talk, I would like to explain also that, in fact, this also whole is again determinantal, provided be bounded. Provided be bounded. So this is what I have explained already. Provided be bounded. But in fact, the main lemma in our work with Xu and Shamov is that this is in fact always determinantal. So lemma, key lemma, in fact determinantal even for all B, for any B. That's exactly right. That's exactly right. That's the whole point. That's exactly right. And by the way, I would like to formulate here an open question, which will become a little bit clear as the talk progresses. So consider just the sine process and take B to be, I don't know, the negative half line. So fix the realization of the sine process on the negative half line. What is the conditional measure on the positive half line? So I don't have an answer to this question. Okay, but this was for the second half of the talk. Now we go back to this, and I would like to see that these conditional measures are different by multiplication by a multiplicative functional. And so I'm ready to formulate the main assumption for this part of the talk. So the main assumption is the division axiom, which in fact I have already written, which we briefly discussed yesterday. So let me call it the weak division axiom, weak division property. So weak division property is the following, that if phi is in L and phi of p equals 0, then phi over x minus p is in L. So let me informally, without a detailed proof, explain why it holds for the sine process. I will just take p equal 0 as well, because in fact if it's proved for 0, by translation it's proved in every other case as well. Why it holds for the sine process and why it holds for a sine process for p equal 0? Well, for a very simple reason. Let's do the Fourier transform. Phi is in L. It's a function with whose Fourier transform has compact support. Phi of p equals 0. It's a function of 0 average. Phi of 0 equals 0. It's a function of 0 average. A function, so phi of x over x, it's the antiderivative. A function of 0 average and of compact support, its antiderivative has compact support. This is quite true. So for the sine process, this is immediately verified. So in fact, one can check, so proposition, and I don't want to do it on the blackboard now, but if you want to see the proof, I have it, just ask me in questions. So proposition, so if pi is an integrable kernel, so I mean integrable in this specific sense. So if pi is an integrable kernel, then in fact satisfies star. Satisfies star. By the way, another proposition, let me just say that integrability, this form of integrability, is preserved by taking Palm measure, is preserved by taking the Palm measure, by taking the Palm measure. Okay. So this is a verification, and let me also say that in joint work with Roman Romanov last year we proved also the converse implication that star implies this form, and in fact also implies that the Hilbert space is the space of holomorphic functions. And that the Hilbert space and range and L is a space of holomorphic functions, It is not, generally speaking, true that it's a space of entire functions because, for example, it's not true for the Bessel kernel. It's a space of holomorphic functions in some neighborhood of the domain of definition. It's a space of holomorphic functions. Okay, now, armed by this weak division property, we can straightforwardly see that just indeed so let me write it in this case. So discrete case. Range of Q is equal to x minus p, x minus q, range of pi, p, q. So shifting the particle corresponds to multiplying the range by this function. Multiplying the range by this function. This is, again, it's like for orthogonal polynomials. So in continuous case, it's even simpler. In continuous case, it's even simpler. I just write that the range, so L of p is equal to x minus p over x minus q, L of q, where L of p is the range of the Palm measure of the Palm kernel, and L of q is, well, the range of the Palm kernel at a different point. And so let me just say that, okay, after these identities with ranges are verified, again, in the generality of integrable kernels, which seem to be the best possible generality because this condition essentially means the weak division property. So once this is established in the generality of integrable kernels, there is the question of multiplicative functional, and this question is tricky, and I don't want to discuss it in detail just to avoid technicality. Let me just say that the approach I have explained works for any kernel of integrable form. However, the sense in which this principal value is taken depends on the specific kernel, and let me illustrate this point on the example of sine, Bessel, and Airy kernel. So for Bessel kernel, this multiplicative functional just converges absolutely. There is nothing to say. For sine kernel, principal value means the usual principal value. One needs to take the product over symmetric intervals. On the other hand, for Airy kernel, Airy kernel has many more particles on the negative half-line than on the positive half-line. For Airy kernel, one needs to normalize, one needs to consider limit and subtract the exponential of the trace. One needs to consider limit over growing intervals and subtract the exponential of the trace. Again, this is very similar to the quite usual Hilbert-Kalimann regularization of the Fredholm determinant, and I just want to say that this trace can quite possibly be, in fact, divergent, as is the case for the Airy kernel, and then this is not defined, but this is defined, and this regularization means just this regularization by the trace, and the argument then, the proof of the relation then just uses, in fact, the small variance property which we discussed last time. Okay, so I claim that I have proved this result. Let me write it in slightly different form. Again, now let me write it for the continuous sine process in slightly different form, but which comes down to the same. So conditional measure of the continuous sine process of the sine process. Corresponding to the following condition, I keep an interval, and I fix the configuration in the complement of this interval. So this I fix, and this I fix. So as we discussed last time, at this point, the number of particles is fixed. The positions aren't, so these are x, I call them x. So the conditional measure, I write it down explicitly. It is some normalization constant. And just for convenience of notation, let me assume that this interval contains 0. Just let's assume for convenience. Okay, so I write, it's an orthogonal polynomial ensemble. With weight of the following type. So how can one understand this formula? How can one understand this formula in the following way? Imagine I consider usual orthogonal polynomial ensemble. For example, I consider just Legendre polynomials. Legendre polynomials. If I consider just Legendre polynomials, so I consider just usual orthogonal polynomial ensemble with uniform weight on the unit interval. And I consider restriction to some smaller interval. Then the conditional measure will have exactly this form because of this. So the statement is that the sine process is orthogonal polynomial ensemble with uniform weight and infinitely many particles. With uniform weight and infinitely many particles. So, and this is the precise form of this statement. So, just that it is possible to pass to the limit. So, how do I say? It is not possible to pass to the limit, for example, in this product. This product is not possible to pass to the limit. It is, however, possible to pass to the limit in these conditional measures. So, and the statement is that if I take, again, Legendre polynomial ensemble on growing intervals, I consider conditional measures, then at the end I get conditional measure for for the sine process. Another way of saying this is that the sine process is almost a Gibbs measure. It is not really a Gibbs measure because the number of particles is fixed here, but it is almost a Gibbs measure, well, with the potential, it's clear with what potential, the Coulomb gas potential, the logarithm of the difference, Okay, so this much for the conditional measures of the sine process and of processes with integrable kernels. And let me now return to the subject with which we started, namely, just go back to the random power series. No? Yes. To the random power series. To the random power series. To the random power series. So, what is the relation between a realization of determinantal point process and the kernel L? So let us recall that we start with the kernel of a projection, so pi is kernel of a projection onto some subspace L. Onto L. And by the Mackey-Soshnikov theorem, there is the measure P pi. So question, what does a realization of the measure, so a trajectory, know about the subspace L? So in fact, Benjamini, Lyons, Perez, and Schramm, and then later Lyons, in discrete setting, proved the following beautiful result in discrete setting, that the reproducing kernels corresponding to particles of a realization generate the whole space. So let me be a little bit more precise. So to the kernel pi corresponds a function, so for to any pi in E, corresponds the function pi p. So this function is in L. And in fact, the inner product with this function is nothing else but the value of the function at P, if f is an L. So this is just the definition of the curve. This is just, I rewrote that f of P is equal to integral pi P x, f of x, d mu of x. Yes? So, so this is just this. This is just this. And so now the statement, the conjecture of Lyons and Perez, is that in fact the span of this pi x over all x in a trajectory in fact coincides with L. In fact coincides with L. So for example, let's consider just the sine process. Let's consider just the sine process. So sine process, as we discussed, a sine process is, so let's consider an example. Example, sine process. Okay, let's see. This I want, and this I want, and this I want too. Okay, so let's consider it here. So example, sine process. Sine process. So this reproducing kernel is just, in fact, the shift of the cardinal sine function. And under the Fourier transform, it just becomes an exponential. An exponential on what? An exponential, of course, on the interval from minus pi to pi. So in this case, and this particular case of the Lyons-Perez conjecture has been settled by Gauche, the statement is the following, that if I take the span of pi of these cardinal signs, so e to the I x lambda over all x in a realization of the sine process, so these are considered as functions in lambda, then this span coincides with the whole Painlevé inner space. Coincides with the whole Painlevé inner space. So I consider the span of trigonometric polynomials, complex exponentials sampled at particles of the sine process, and this span is precisely the whole Painlevé inner space, the whole space of compactly supported, the whole space of L2 minus pi pi. So this system is complete in L2 minus pi pi, and this case has been treated by Gauche. So in fact, Gauche proved the Lyons-Perez conjecture under the assumption of rigidity. Proved under the assumption of rigidity. And Lyons, as I said, Benjamini, Lyons, Perez, and Schramm, and Lyons himself proved in the discrete case. And we proved in joint work with Xu and Shamov, we proved for the general case. So with Xu and Shamov, we proved for the general case. So, and indeed, the first case, which is not covered, first important example that is not covered by the formalism of Gauche is the precisely the case of the random power series. So the case of determinantal point process corresponding to the Bergman kernel. Where the range is precisely, range K is precisely the Bergman space, the space of holomorphic functions on the disk, square integrable with respect to the Lebesgue measure, the space with which we started our lectures. So, and then the statement is, and with this we have started, the statement is that a realization of the Bergman process, which by the Peres-Virac theorem is precisely the random zero set of a Gaussian analytic function on the disk. So this realization is almost surely a set of uniqueness for the Bergman space. So this conjecture can equivalently be formulated as follows. So as two equivalently be formulated as follows by saying that if f in L in restriction to x is equal to 0, then f is in fact identically is equal to 0. So that almost every realization of a determinantal point process is the uniqueness set for the corresponding reproducing kernel Hilbert space. Okay, Let me now say very briefly the key ingredients of the proof. So very briefly, and then I will, in the remaining time, I will say a few words about a question of interpolation. Okay, let us go up here and go down here. Yes. So the key lemma, as I said, is that the conditional measure of a determinantal point process is itself determinantal. And one might think that this statement is a complete triviality given what has been said so far. So we have seen that conditioning on bounded sets preserves the determinantal property. Well, we all learned the Martingale theorem in college. End of proof. Except no, because the determinantal property is not, in the continuous case, closed under weak convergence. And so it is possible to construct determinantal measures with a non-determinantal limit in the continuous case. And furthermore, as I mentioned previously, the connection between a determinantal process and its kernel is quite delicate, and therefore it is not clear how from convergence of determinantal measures, even imagine we know that a sequence of determinantal measures converges to a determinantal limit. Given a sequence of determinantal measures, it converges to a determinantal limit. Is it possible to say that the kernels also converge to a limit? So this is completely unclear. So the kernel uniquely defines the measure, but the measure does not define the kernel. And it is tricky. So in fact, we prove with Xu and Shamov that we use the Martingale theorem, but it is useless for us to use the Martingale theorem for these measures. They are, of course, form a Martingale, but it is useless for us. So we take the kernels of these measures, and let me just formulate this very imprecisely. So very imprecisely, let me say is, so I put is in quotation marks, so is a Martingale. This needs to be made precise, is a Martingale. So this is what we check. And then, of course, there exists a limiting kernel, which is the limit of the prelimit kernels, and this is the main point in the proof of this theorem. So, and this I don't have time to explain in greater detail, but let me just say the very end of the proof. So given that we have constructed the conditional kernels, let me explain how the proof concludes. So conclusion of the proof, given the key lemma, so key lemma to theorem, this I can explain. So how does the key lemma implies the theorem? And in the following way. Just imagine there exists, imagine in contradiction there exists such a function. There exists such a function. There exists a function which is zero, such function f, which is zero everywhere at all particles, but itself not zero. Choose some interval without particles where the function is not zero. Conditional measure on this interval provided fixed environment here, fixed here, fixed here. This conditional measure is, again, a determinantal measure governed by conditional kernel. If this is interval I, it is governed by the conditional kernel, which we k x complement to I. Okay. This is conditional kernel, which we have by the key lemma. Now comes the main point. This interval does not have particles. But then, by Fubini's theorem, the conditional probability assigned by this conditional measure for this interval not to have particles, since there is this very realization, which does not have particles in this interval, by the Fubini theorem, almost surely the conditional measure of this, with this condition, that there be no particles in this interval, is positive. The conditional measure, the gap probability, we know, we have discussed this in detail, is determinant 1 minus k x. So it is positive by Fubini theorem, because again, since this our very realization has no particles in I, the conditional probability fixing our realization that there be no particles in I must be positive. So it's positive. At the same time, because of the formalism that has been developed so far, and because of the martingale property, let me stress it, on the level of kernels and not on the level of measures, I can say that the function chi I f is in fact invariant under the kernel. Because please observe, conditioning corresponds to taking zeros and restricting. Take 0 and restrict, take 0, restrict, take 0, restrict. But this function has 0 at all particles, and well, it is supported on this I, so it is 0 everywhere beyond. So precisely it is fixed by this operator, by the limit transition, because the limiting operator is the limit of the prelimit operators. But if an operator has eigenvalue 1, then determinant 1 minus operator is equal to 0. And if a number is both 0 and positive, then this is a contradiction. So, and this concludes the proof. This concludes the proof of the Lyons-Perez conjecture from the conditional measures of determinantal point processes. So, in the remaining 1 minute, I will just very briefly say that the question remains, and let me refer to the joint paper with Xu, just a preprint on the archive. The question remains just how to recover. So I say a Bergman function can be recovered from its restriction on this random configuration. But how to recover this Bergman function? So, and this question, we have some partial progress, which I'll say right now, but it remains largely open. But, so it is really not clear, the question remains. So how, so we know that this set is uniqueness set for the Bergman space. Any Bergman function can be recovered. But let me just say that in some situations, it is possible to recover the Bergman function using the Patterson-Sullivan construction. So, and in fact, one recovers the Bergman function from this realization by writing f. So the realization is x, and I write this formula and we conclude. So x, I want to recover it at a point z naught. So, and I write f of z naught is equal to the limit s goes to 1 sum e to the minus s distance. Distance is, of course, means the Lobachevsky distance. So dx z naught f of x, x are in the configuration, times sum e to the minus s d x z naught, sum over x. And so again, let me say the details are in the paper, it's on the archive, that this allows one to, in some situations, to recover a Bergman function from its values to a random realization of our point process, from a random realization from a random zero set of the Gaussian analytic function. Thank you very much.
Thank you very much. Any very quick question?
So I'm not wrong if I say that if pi is a finite range projection, then Lyons-Perez conjecture is obvious.
Yes,
yes, okay.
That's correct. In fact, the range is, so it is supported. So if I consider finite range projection, then the weight of corresponding configuration is the corresponding determinant, and it is 0 precisely when the functions are linearly dependent, when the Vronsky determinant, essentially, and it is 0, so yes. So it is somehow tautological in this case, yes.
Any other questions?
Yes, there is here.
Yeah, just thinking about the
Just 1 second.
So just thinking about the conditioning, the conditional measure.
Yes.
So you gave the heuristic for the orthogonal polynomial case.
What do you mean heuristic? I gave proof. I gave you proof for orthogonal polynomial.
Yeah, no,
I don't give heuristic. I give proofs.
The formula for the orthogonal
Yes.
polynomial case. In that case, you see from the formula without.
Excuse me, say again?
From in the orthogonal polynomial case.
Yes.
You see from the formula that you have again an orthogonal polynomial ensemble.
Yes.
So
yes.
I guess it's the same for the in the Pfaffian case.
Yes.
Are there
Yes.
analog of this general theorem?
Yeah, I think this is a very good question. So in fact, I think it is a very good and realistic question. So the problem is again with Pfaffian processes, we don't know any existence result. We don't know why Pfaffian processes exist. But once they do exist, it makes perfect sense to ask whether these operations preserve the Pfaffian property. So the analog of this can be checked. So how to say, the height times length equals area is true for quaternion determinant as well. So this one can check. Then, for example, this, I think it would be a very interesting and realistic question to do this. So we can discuss more privately, yes.
Anything else? Well, if not, I think we can call it a day and thank Alexander again.